Last section, chapter number 3, reaction kinetics. The reaction kinetics, it is the rate at which a reactant is consumed and a product is formed. So if you have like a reactant that is being consumed to produce a product B, this reaction is controlled by a reaction kinetics. Of course, we have to understand what is reaction kinetics, and this is the rate at which the reactant is consumed and the product is formed. And there is another definition for reaction equilibrium, the state in which the concentration of both reactants and products no longer changes with time. There is no longer of a change of concentration of reactants and product. Example of these kinetics is activated sludge in wastewater treatment plant and, of course, chlorination. Why we need to understand this reaction rate? Because we need to understand the reaction stoichiometry. We need to know the reaction order, first order, second order, zero order, and of course the numerical value are very important for all rate constants. Let's look at this simple reaction. Let's see, we have, remember when we talk about methane, it's C with 4 hydrogens. Now, when this is gone, and this is gone, and there is a chlor, instead of that, we call this dichloromethane, DCM. So if dichloromethane, DCM, is reacting with OH, you can see that OH will kick one of the chlors and replace it, and you can see that the Cl- will be freely in water. So the rate reaction of this equation or this chemical reaction, it's K. K is the rate constant for this reaction, concentration of DCM, dichloromethane, times concentration of OH minus. This is the rate reaction. Now, this is also equal to minus D, the change of DCM with time, minus D, concentration of DCM with time, dt. Same thing, it is equal minus change of OH minus divided by dt. Also, the minus, it means they are being consumed, they are being disappeared, or they are being decreased over time. And then plus dCm over dt. Now, this is the change of Cm over dt, or dCl minus over dt. Remember, here there's pluses because there's forming, and here there's minus because they are being consumed. The rate law is very important to understand, especially when you are dealing with reaction kinetics. And this rate law expresses the dependence of the reaction rate on the concentration of the reactant. Let's say if we have this reaction. So the rate law is written as K, A, concentration of A to the power. This one should be A, times B, chemical B to the power Y. Let's say this is going to be Y. Okay? This is going to be Y. So it's going to be reaction rate R in mole per liter per time is equal K, concentration of A to the power A, times concentration of B to the power small p. And all these are the units for each one of these parameters. So when you put this reaction rate, you can see that there is something called the order of the reaction, which is the sum of these two. This is the order of the reaction. A plus B is the order of the reaction, which is the sum of all the powers in the rate equation. Of course, this is an elementary reaction, and not all reactions are elementary. Since we are doing with for rate reactions and reactions, we have to start with the first reaction, a zero order reaction. Not all chemicals are following zero order reaction. Some chemicals will follow zero order, some of them will follow first order, and some of them will follow second order or third order, and some of them will follow some weird forms of reaction rate, and we'll be talking about this in the next few slides. The zero order reaction, it means that dC over dt, the change of concentration with time, is equal minus K. Look at this, C to the power 0. It's a zero order. And this is going to be equal to 1. So dC over dt is equal to minus K. This is the equation for the zero order reaction. If you take dC, take the delta T the other side, so you could integrate this and integrate this. This is from C naught to C, and this is from 0 to T, from the start of the experiment until time T. And then you could integrate, you will get this one. C at any time T, of course, equal C naught initially minus KT. So this is the equation for the zero order reaction. C naught is the concentration at time T, and let's just put CT is the concentration of C at time T. Time half an hour, time 2 hour, time 3 hour, of course, and T will change with this T. And K is the rate constant with units of mole per liter per time. Okay, now the first order reaction, same equation, but here you put to the power 1 minus K to C to the power 1. You integrate, you'll do the same thing. It will be ln C over C naught minus KT. You could rearrange it. It will be giving you the following equation. Of course, this is C time T. CT. C at any time T is equal to C naught e to the power minus KT. C naught is the initial time at time 0, and CT is the concentration of C at time T, and K is, look at this. If T is in time, K has to be 1 over time. So K has to have a unit of 1 over time in order to cancel out with the T2. This table will summarize all the equations for the zero order and first order. You can see this is the rate law for this, and this is the rate law for the second one, first order. This is the integrated form of the rate law, and this is the integrated form for the zero, and this is for the first. If you plot time versus C for the zero order, you'll have a straight line. And why it is negative? Because you can see the sign. This is a reduction. It's going down. Okay. The intercept is C naught. This is the intercept, and the slope is K. As you can see, the K is the slope, because this is equivalent to Y equal B plus MX. B is the intercept, and M is minus K. M is the slope. There is no need to linearize it, because for the zero order, it's almost linear, should be almost linear, and you should have the best fit for it. And now, to find out the half-life, the time of the half-life, what is the meaning of half-life time? If you have a tank, and this tank has organic, let's say that has 100 milligram per liter TCE. If we need to know the time it will take this 100 milligram TCE to go to 50 milligram TCE, we call this half-life. Half-life that goes into 50% of the concentration. So the half-life is 0.5, the initial C naught over K, the rate constant. And of course, the unit of K is milligram per liter per second, or mole divided by liter per second. Now, for the first order, if you are plotting time versus C, it will not give you a straight line. It will give you a curved line like this. Okay? And of course, this curved line, we cannot get any information out of this. We have to make this one linear. So we should take this equation and make it linear. You should do a ln C equal ln C naught minus KT. So this is the slope. Time is the y-axis. This is y. And this is B. So T is the x-axis and y is ln C. So T is the x-axis and ln C is the y-axis. And then when you plot it, the slope is minus K And of course, you can see it's going down. And the intercept is length C naught. The intercept with the y-axis is length C naught. And you could find out all the parameters out of it if it's first order. To find half-life, if the reaction is first order, you should get this equation, 0.693 over K. As we said before, K is 1 over second, 1 over minute, 1 over hour, 1 over day, 1 over time. Pseudo first order reaction, it is, of course, there is a lot of times that the concentration of one of the reactant remain constant during the reaction. For example, if the concentration of one reactant is initially much higher than the concentration of the other, if the concentration of one reactant is buffered at a constant value, example, pH in the lake. So in this one, we have to use the pseudo first order reaction. Let's give you an example of one of these first order or zero order equation. How long will it take to the carbon monoxide, okay, concentration in the room to decrease by 99%? So there's the room in the house. Let's say this is the room, okay, and you want to reduce carbon monoxide by 99%. 99% after the source of carbon monoxide is removed. So there is, for example, there was a heater, and this heater was emitting carbon monoxide, and then you find out there is a high amount of carbon monoxide. Now you stop this, and you want to allow the carbon monoxide to be reduced by 99%. So after how long a time to decrease by 99% after the source of the carbon monoxide is removed? And the windows are open, so you open the windows. So air is in and air is out. How long it will take this carbon monoxide to reduce by 99%? Of course, by this, we should assume that carbon monoxide follow a first order rate constant, CO removal, of course, due to dilutions by the incoming clean air, and which is 1.2 hours. This is the constant K. The K, this is the first order rate constant for CO, carbon monoxide removal rate. And of course, we're assuming that there is no chemical reaction. Nothing will react with carbon monoxide. So carbon monoxide will not be removed, will leave the house by the ventilation. So let's look at this. First order, we have to put the equation, CO time is equal. Remember, if you go back to the equation, CO initial, E minus KT. So I'm going to follow up. I'm going to do this. I'm going to follow this equation. Okay? C at time t is equal C naught E to the power minus KT. Okay. So now, in order to remove 99% of carbon monoxide, I'm going to put, look at this. I'm going to assume that C naught is 100. Okay? So, initially, if you have 100, what is 99% removal of 100 to have CO final or CO at the time needed? Should be 1. 99%, they should have be CO 1. So, CO at time t is 1, CO initial is 100. And then E to the power minus K, K is 1.2 per hour. And of course, the time that needed that we want to do at the end. So now, 1 over 100 is equal E minus 1.2 T. And then you could do ln and 1.2 T in a minus. So ln 1 over 100. And then T is equal ln 1 over 100 over minus 1.2, and you will get the answer 3.8 hours, which means it will take 3.8 hours for this carbon monoxide to clean up from the room. If you are wanting 99% removal of carbon monoxide from the room. The pseudo, I will let you do this in your own because it's simply the same thing, and you could redo this in your own if you want to. So let me look, and also this one's very simple. Assume that BO4 3- is removed from a municipal wastewater through a precipitation with Fe3. So you put this Fe3 plus, and you precipitate the BO4 3- according to the following reaction: BO4 3- plus Fe3 plus. It will precipitate. You can see this one will precipitate. If you add this to this will precipitate FeBO4 solids. And if you want to do the reaction, it's dBO4 3- over dt is equal minus K Fe3 plus BO4 3-. Okay? So, look at this. Here there is nothing. 1 and 1. So what is the reaction order of this reaction? It's 2. 1 plus 1 is 2. What order in this reaction is overall? Secondary. Or second. Okay? So, half-life, we did explain this. Half-life is explained as the time required for the concentration of a chemical to decrease by 1/2. We did mention this zero order. This is the equation, and this is the way we derive it to find the zero order half-life. Same thing for first order. It's this, and you could follow the derivation of it. Now, let's look at the following examples in order to classify and clarify the reaction rate. Subsurface half-life of benzene, TCE, and toluene are listed. So he gives you the half-lives. So he gives you half-life for benzene, TCE, and toluene, respectively. We'll do one of them. What are the first order rate constants? He wants to know K, constants, K, for each one of them. What are the first order rate? Okay, so here, remember T half for this is the first order. T half is equal 0.693 over K. That is the equation of T half. For this one, you could put the K here and put T half here. So this is K is equal T half. So we're going to put 69. We're going to put it here. And 0.693 is constant, so you'll get 0.1 per day. This is the rate constant for benzene. You could find TCE, and you could find toluene easy. Use of half-life for determining first-order decay. This is also for you to look at, which is it's the same equation, even though that they have something weird here. But you can see CS at time 5 days, CS at time 0, e to the power minus kt. It's the same process, so I think this one is also for you to look at. What I need to show you, because this equation, we call it Monod equation. And Monod equation is very important once we study biological treatment. In some cases, biological reaction, the rate of behavior may vary differently over a range of concentration. A as a reactant. Let's say that minus Ra, the consumption of A, that's why it's a minus, is equal K, rate constant K, Ca, concentration of reactant A, divided by Ka, half saturation constant, plus Ca. And this behavior of the variable was designed by Monod in 1949, which give an evidence that bacterial growth and decomposition of waste follow a variable order rate expression. So you can see that as you increase the concentration, the rate reaction will increase until it reach a maximum. And this maximum is K, and K is the optimum here. So half of this K, you could find K over 2, and this K over 2, you could find Ka. Okay? So this is K. Okay? Half of it, we'll find out Ka for you. So this is the Monod equation. That's the Monod derivation. I don't want to go deep into this because we'll keep this for the master's degree class. And this Monod equation, we use it a lot in environmental engineering practices. So the variable order reactions, if you have minus Ra, Kca over Ka plus Ca, If the concentration Ca is much lower than Ka, so which means that Ca is very small, you could cancel it. So it's going to be K, small k, Ca over Ka, and that is almost a first order reaction. So if the concentration Ca is much lower than Ka, so it's a first order reaction. At high concentration, when Ca is much bigger than Ka, so that now Ka is 0. And then Ca will cancel out with Ca, you will have K. Now, if at high concentration, it is a 0 order reaction rate. Okay? And anyhow, temperature will affect rate of constant. Like humans, there is an optimum temperature. Beyond that, the rate constant will decrease. And this equation, Henry's equation, will determine for you the rate constant at different temperatures. Of course, you could see here in the derivation of how to find the effect of temperatures on rate constants. What I want you to know that this is the equation that we use a lot. If you have a rate constant and something changed in the reaction, let's say K1 is at this temperature, and the temperature 2 was changed, you could find K2. Of course, provided theta is constant. Theta is being found for us, for biological processes, biological decay, from 1.056 to 1.13. So this is a range for theta. So you could see it. Let's see, I chose 1.07. So K2 is equal K1 times 1.07 to the power T2 minus T1. Okay? Let's find the effect of temperature on carbonaceous biochemical oxygen demand rate constant. The rate constant for carbonaceous biochemical oxygen demand, CBOD, at 20 is 0.1 per day. Okay? So K at 20 is 0.1 per day. What is the rate constant at 30? Look at this. You go from 20 to 30. What do you expect? Heating, when you heat up the reaction, you will increase the rate. So he's saying here to assume the theta is 1.072. At that time, I assumed it 1.07, but you could do it 1.072. That's an assumption, because most of the time it goes from 1.056 to 1.13. So K 30 is equal, remember the equation? K1 is 0.1 per day times theta 1.072 to the power T2 minus T1. T2 is 30 minus 20. Now you could find this. This would give you 0.2 per day. Almost doubled. If you go from 20 to 30, you are doubling the reaction rate. Okay? This is also another quiz that you want to look at. If you have nitrogen dioxide, NO2, concentration are measured in air quality study, and decreases from 5 ppm to 2 ppm in 4 minutes with a particular light intensity. So you have reduction from 5 ppm to 2 ppm in O2, nitrogen dioxide, in 4 minutes. What is the first order reaction rate for this reaction? Remember, from this you could find out it is a first order or zero order. So it decreased from 5. You can see that this is a first order. So NO2 at time t, NO2 initial, e to the power minus kT, and finally it was 2. Initially it was 5, e to the power minus, we need this, and we have t, 4 minutes. Now k is going to be 1 over minute. So when you solve it, it will be 0.23 per minute. Here he has the first order. What is the half-life of NO2? Now half-life of NO of first order, it's 0.693 over K. K is, we just found it from here. You just put it 0.23 per minute, and this would give you 3 minutes. After 3 minutes, you will get 2.5 ppm, because initially it was 5 ppm. To give half-life, to give 2.5 ppm, it will take 3 minutes. Let's look at the last one. What would be the rate constant needed to be changed in order to decrease the time required to lower the NO2 concentration from 5 to 2 in 1.5 minutes? Okay? He need to know the rate constant K. So let's look at this. So he need NO2, What is NO2? From 5 to 2 minus K, 1.5 minutes. So if you plug it into the equation and find K, the K would be like this. Okay, so 0.61 per minute, the K. Look at this 0.23 and look at this 0.61. Well, I will leave you with all these examples because they all go around the same concepts and the same techniques. So it's good to look at them, and hopefully you will enjoy solving these problems. Thank you very much.